Okay, lecture number 4 here. What I want to talk about, I talked last about storing energy. Now we're going to talk about transferring energy. Energy transfer. And in this class, we're pretty much going to talk about energy transfer of one of two important categories. Heat and work. Okay? Heat and work. We're going to talk about heat transfer, we're going to talk about work transfer. Okay, now, before we get on to the specifics, I want to talk about sign convention because this is something that gets students very confused. And unfortunately, I've added to the confusion by making a mistake in your notes, so let me fix it right now. The sign convention. Throughout the class, we will say that heat transfer into a system is positive. Yes. And work out of a system, I said negative, but that should be positive. But how about we just redo it this way? We'll say instead of out of, we'll say work into a system is negative. That's what it should have been. So work in is negative. Heat transfer in is positive. Now you might ask yourself, why do we have that sign convention? Why don't we say both of them in are positive and both of them out are negative or something like that? Why do we have this thing where the sign convention for heat and work is different? Okay, here's why. Generally, what I want to do, my goal, my biggest goal in thermodynamics is this. I want to take heat into my system and I want to make work. That's it. That's generally what I want to do. I want to take heat and I want to turn it into work. That's my most likely definition. Now, that's why it's positive. Okay? Positive, heat in, positive, work out of a system. That's why it's that way. Now, you can go the other way. If you have a system that takes work and gives you heat, the work in is negative and the heat out is negative. Okay? But on a day like today when it's cold, that's not all bad to take work in and get heat out. In fact, if you have a space heater in your home, that's exactly what it does. Because as I explained before, one form of work is electrical energy. Whenever you plug anything into the wall, you get work. You plug it in, it gives you work. We call electrical energy, electricity, right? But it's basically thermodynamic work. And if you have a space heater, it gives you plug it in, so you put work into the heater, and it gives you heat. You're happy to do that on a cold day. But from a thermodynamic principle, that's not what it's all about. Because we can always do that. We've been able to make heat for a long, long time in the world. Think about how many thousands of years we've been able to make heat. It's not that hard, okay? It's much harder to make work. So it's harder to make electrical energy, to make stuff go. That's much more important. And that's why we put it as a positive. We want our systems to make work from heat. That would be a lot better. Okay? That would be a lot better. Because you can always make heat. But it's the positive direction that's harder to do, but also more critical for us. Okay? So let's talk about the two forms. First one's pretty easy, heat transfer. In this class, we're going to designate heat transfer with the letter Q. We're always going to use Q for heat transfer. Okay? That's our symbol for heat transfer. And again, just to denote, it's going to be, if it goes into a system, we're going to call that positive. If it comes out of a system, we're going to call that negative in our sign convention. If I write it per unit mass, I write it as a lowercase q. And basically that's heat transfer per mass. And of course those units would be joules per kilogram or BTU per pound mass. Okay? Now, there are three basic forms of heat transfer. anybody know one of the forms of heat transfer? Conduction. Yeah, that's a good one. Conduction. Conduction is one form of heat transfer. Conduction occurs when two bodies are in physical contact with each other and heat is transferred from one body to another body. You have to have physical contact to have conduction. Okay? It's a direct physical contact between two bodies, one transferring heat into the other one. That's conduction. Okay? Remember any of the others? Radiation. I'll call that one number 3. What's that? Induction? No, that's not heat transfer. That's something else. Convection. Yes. Conduction, convection, radiation. Now, convection occurs when heat transfers through a fluid. The most common ways in which you see that is if you were to cook something by boiling it or frying it. Okay? Why does frying cook something up so fast? Because a hot oil transfers heat into an object much, much faster than hot air. Okay? Okay? And even hot air, if you have a convection oven, right? You might have a convection oven. What does that have? Basically, it's an oven with a fan on it. The fan just moves the air around and creates a convection. Okay? Yeah.
Convection would be like radiator.
Heat
goes from the engine to the radiator.
Well, the fins, obviously the fins of the radiator to the air blows over the radiator on the fins, and there is convection through the air blowing, yes. But there's also conduction, because the conduction between the radiator system and the engine can be there's a lot of conduction and convection as well. I mean, they're both happening, really. So, yeah. But convection has to have a fluid. That fluid could be air or water, okay? All right. But it has to have a fluid. Basically, it's a very good form of heat transfer, though, okay? You can cook something a lot faster in a fluid than you can in air, okay? If you have still air, or you have a plate that's just, grilling or something like that, that's a lot of just, conduction. But you can cook real fast if you boil it or put it in oil or something like that. Convection will cook much, much faster. Then there's radiation. Radiation is a heat transfer between two bodies that does not have a medium between them. Okay? So you can have radiation without having air carry it or anything like that. It's a direct heat transfer. One of the most common ways we see radiation heat transfer, radiative heat transfer, is on a cold night. If you know, a cold, clear night, the temperature will drop much faster than a cold, cloudy night. Okay? If it's cloudy at night, you will have much less of a temperature drop outside. Because what happens on a clear night is that the Earth's surface radiates with the atmosphere, with space, essentially. And if you know anything about space, it's really cold out there. And so it radiates literally with hundreds of miles up in the atmosphere. Very, very cold. Okay? So it draws a lot of heat directly out of the Earth and out of buildings and things like that. Okay? That's radiation. But if you have cloud cover, then you're only going to radiate a little bit with the clouds, which are not nearly as cold. Okay? So, and you can feel radiation heat transfer with a large bonfire, things like that. You can feel convection from it too. But in anything that has a lot of heat, a lot of times you feel that radiation. Okay? It's direct transfer. So, sunburn, the sun is pretty much radiative. Of course, yeah. The sun carries energy to the Earth. It doesn't need air to carry it. We're not touching the sun. It's obviously all radiation. So, yeah. Okay, so those are the 3 main forms of heat transfer. We have a whole class dedicated to heat transfer, so obviously it's important, but we're not going to do a lot with it in this class. Basically, in this class, all you need to know is there's heat transfer. It's pretty much either going to be a given or you're going to solve for it based upon some other equations. Okay? But it's never going to be something where you're going to have to do a lot of thought on as far as like what it is and all that kind of stuff. We're not going to quiz you and go, oh, is this radiative heat transfer? No. we'll leave that for heat transfer class. Okay, I'm just telling you now just to kind of give you background. Okay, work transfer. We're going to call work W. That makes sense, right? And again, it's negative in because I don't really want my machines to take work. I want my machines to give work, so it's positive out. That would be the ideal case, at least. Again, I can express it as a lowercase w as work per unit mass. Those units could be, again, joules per kilogram or BTU per pound mass, whatever, right? Okay. Now, real quick, I want to go through some forms of work that we're going to see. One, you get work every time you have a volume change. Okay? Now, we'll discuss the particulars of that later. Okay? But let me just give you this scenario. I want you to visualize this, because I think most of you can visualize this. Think of a piston cylinder assembly. Okay? And think here, this is going to be an air-fuel mixture, right? Inside your piston cylinder. And then what happens? If it's a spark ignition engine, you have a spark, right? You have a spark. And then what happens? You have an explosion, basically a controlled explosion inside your engine. You have a lot of them, right? That's how many cylinders you have and the speed and all that stuff, but Okay. What happens is that when you have the air-fuel mixture and you have that spark, you have what we call expansion. You have a significant volume change in that cylinder. What happens? The piston will go up, all right? That's a volume change. In fact, a lot of times we rate engines by how much volume displacement they have, okay? You might see stuff called like a 5.0 or 5.7 liters of displacement. Engines are rated that way, right? They're rated on their volume change. Volume change is work. Work is, work per unit time is power, okay? Now, we'll get more into the particulars of that later, okay? But we'll just say for now it's volume change, okay? Second form, electrical. All you need to know with that one is that the work electrical is equal to the voltage times the current, VI. Hopefully you know that from your physics. Electrical power, now that's W dot. Remember when I put a dot over it, it means per time. So that's power. Electrical power, or work per unit time, is voltage times current. Okay. So if you have a problem in the future that gives you a voltage and current input, you know that's an electrical input, that's a work input. Okay. Third one, mechanical. Okay. Technically, it would be the integral of f dot ds, but remember, we're not going to do integrals in this class. So basically, what we're going to say in this class is it's force times displacement. Force times displacement. S is displacement. Okay, let me wrap this up here real quick with the last two. Another one we'll have is springs. Spring work, you should have seen this before, I'm guessing a little bit in physics. 1/2 K x2 squared minus x1 squared. That's the work of a spring. Has to do with its displacement of the spring. 1/2 K times x2 squared minus x1 squared, where x2 and x1 are the positions of the spring, right? Okay. And lastly, real quick, the output of a lot of engines and systems like that Basically, they all go to a rotating shaft that would then be part of your drive train. So we call it shaft work, and that is equal to 2 pi n dot times T. And let me just make sure you know, T is torque, and n dot is the speed of the engine in revolutions per second. Kind of like RPM, but this one's RPS. Okay, that's shaft work. Okay, these are all forms of work either into or out of a system. Okay, there's more. This is not an exclusive list. There's more, but that's going to give you some. Next time we define the first law and we put everything together.